of the fourth analysis, where we are continuing to solve more examples on fourth analysis. Let's look at another example where there is a fault on phase A to X. It means that there's a line to ground fault. So we basically have a three-phase generator. So we have a generator connected through a feeder, and the feeder there's a fault at the end of the feeder, and the fault is a line to ground fault, right? And then the generator, the positive phase, negative phase, and zero phase have been given, and the feeder positive phase, negative phase, and zero phase. So actually, the X1, the X2, the X0 for the generator, the X1, the X2, the X0 for the feeder has been given. So this 2.5, their reactances, so J 2.5, and then J3, and then the generator is J1, G 0.7, and G 0.3. So basically, this is what has been given us, and we are supposed to find a line to ground fault. And we have learned that line to ground fault, we need to find the PPS, the NPS, and the ZPS impedances, and I'm basically going to put them in series. In series. Now, basically, in this problem, we have been given that a three-phase generator with a solidly earth. So we just have to know the earthing system. Anytime the fault is to ground, you have to note that. If the fault was not to ground, I wouldn't have cared about the earthing system of the system. So the relevant reactance of the generator and feeder in ohms are given in the table. So everything is already ohms. So it means that we have been given the generator line to neutral voltage. It means that the phase voltage, V phase, has been given as 6400. It means that its actual values, we continue to work with the actual values, right? So basically, we have the fault at this end. So I may need my PPS values. My PPS, I basically have my generator here, then the reactance of the generator, then go to the reactance of the feeder, and the fault is here. Here was given as J1, and this was given as J.25. And I'm basically picking the 1 values because the 1 values are the positive phase sequence values. So with this, you can easily see this and this are in series. So X1 happens to be J3.5. Now let's find the NPS. The NPS, I'm also going to draw a line without any generator. Bring the reactance of the generator, the reactance of the feeder. The fault is here. This was given as J0.7. This as J2.5. So my X2 will end up being J3.2. And let's look at the zero phase sequence. Now with the zero phase sequence, so I draw my line, then I need to know the grounding system. You notice that when I was doing PPS, NPS, I didn't worry about the grounding system of the generator. But zero phase sequence, realize at this point, we have already explained why we need to cater for the grounding system of the generators and transformers within the circuit. So they start grounded. So what it means that I'm going to basically start from the line and bring the reactance of the generator, go to the reactance of the feeder, and then the fault IF is here. The fault is here. This was given as J0.3. This also as J0.3. So my X2 happens to be this and this in series, which will be J. This was actually given as J3, not J0.3. J3, as seen here, it was given as J3. Good, but then the generator X0 was given as J0.3. So this gives me J3.3 as the reactance for the X0, that's zero phase sequence. So we are using 0 for zero phase sequence, 2 for negative phase sequence, and 1 for positive phase sequence. So basically, I'm going to have my E, which was given as 6400 here. My X1, we just calculated that, is J3.5. My X2 is J2, we got 3.2. And my X0, we got J3.3. So I'm basically going to find I0 here, which is going to be E on X1 plus X2 plus x naught, and this was given as 6400 over x1. We got j 3.5 plus j 3.2 plus j 3.3. So this basically give me x naught as minus j640, and we said the fault current for line to ground fault is 3I0. So 3 times minus j640, this gives me minus j1920. And in terms of magnitude and angle, I'll get this angle minus 90, and this is my fault current. It means in terms of magnitude, the fault current is basically 1920 amps. And this is basically how we solve the such questions, right? So very simple. Let's look at a more complicated example. So let's say we have a system like this, very large network. So we basically have a generator, and the question actually says that we have a 25 MV 11 kilovolt. So this is a 25 MV generator, and the terminal voltage is 11 kilovolts. It's supplying two motors. So the two motors are here through two transformers. You have transformer 1, transformer 2. The one line diagram of the system is shown below. Now, if a double line to earth fault occurs at point G, we are saying that there's a fault here, but the fault is a line to ground fault. So we know the type of fault, right? And then we said that it's occurring between phase B and phase C. We've explained with such an example. Now find the fault current given a fault path resistance. So we are saying that this fault, the fault has a reactance instead of a resistance, was given as a reactance. The fault has a reactance of J. So let's draw that well so that we know what is actually happening. Because it's very important since the fault has a reactance to ground, and that is given as J 0.1. So we should not forget this reactance. Good. So let's see how we are going to solve that. First of all, I know that this is a line to ground fault. So I need the positive phase sequence, the negative phase sequence. And because it's ground, I also need the zero phase sequence. And we have actually discussed that anytime that I have a line to ground fault, this is how my network is going to be. My E is going to be here. My X1 is here. And I'm going to put it in parallel with X2, right? And then I'm going to have X naughts here also. But in case the fault has a resistance or reactance to ground, like this example, the fault part itself has a reactance, XF, I would have to bring 3 times the XF. If it was resistance, it would have been 3R. Need to be inserted where the zero phase sequence is. That's when you need to know when the fault has a reactance. So note that. So we just need to know from the power system what X1, what X2, and what X0 is. Good. Now let's find that. How do I find my X1? Let me do my X1 just here. That's my PPS value. Let me start basically here. I draw my line. Now you realize that here we have a generator. I bring my E. Then you realize that I bring the reactance of the generator. Now with this power system, from the generator, it goes to the transformer, it goes to the line, goes to the next transformer, and then to the two motors, right? So now I'll have the diagram drawn like this. So this for the generator, then I go to the first transformer, then the line, the next transformer, and I have two motors in parallel. So let me draw them like this, and then like this. Here you can decide to put the motor voltage as part of the PPS, doesn't really matter. So you realize that these were the parameters that were given for, let's look at the problem. You see, we have been given the X1, X2, and X0 for the transformer, the X1, X2, X0 for the next transformer, the X1 and X2 for the generator are the same. So let me start with that. So I'm picking the X1 value. So first, the generator is J0.2. So I put J0.2 here. I come back. The X1 for transformer 1 is J0.0805. So J0.0805. Then I come to the line. When you go, the line, the X1 is given as this. I pick that to J0.6164. Then the X1 for the next transformer 2 is given as J0.0805. Then the reactance for this was given as J0.345. And this particular one was given as J0.69, right? Now you realize that the fault is after the transformer. So you realize that the fault after the second transformer, the fault point is here. So the fault point is here, then what will be the total impedance in this? And basically, when we are finding X1, X2, X0, it's basically the Thevenin's reactance. So it's assumed the voltages are all shorted. So we can see that this and this, the two motors will be in parallel, and then their reactance will be together like that. And then this, and this will be in series. And after that, they will be in parallel with the answer that we got here. When you do that, so you are going to get J0.2 plus J0.0805 plus J0.164 plus J0.000805. This answer, you're going to put that in parallel with J0.345 in parallel with 0.69. So basically, this is how the total reactance is going to be. And when you compute that, you're going to get X1 to be J0.16. You can easily take time to compute that to get X1 to be that. Now let's look at how we find X2. The same approach, the same approach. And luckily, but mainly you just have to make sure that you are picking the values. The X2 value for the generator, the X2 value for the transformer, the X2 value for this, and the X2 value for this happen to, and then that of the motor, the two motors, all of them happen to be the same as the PPS value. So just that you still need to draw the diagram, right? So starting with that, you have to bring no voltage source because you are doing NPS. So you bring the reactance of the generator, then go to the transformer, the line, the next transformer, and then the fourth point is here. Then you have your two motors where you can have the reactance of the first motor A here and the reactance of motor B here. Good. So basically, in terms of the NPS, the values were the same. Here was J0.2, J0.800805, J0.164. Here is J0.0805. And here was given as J0.345. And we have here as J0.69. So the same way, all these are in series, all these are in parallel. You put them together, you're going to get X2 to go to J0.16. And this is how we get our NPS value. Now let's look at the zero phase sequence. The zero phase sequence. The zero. And you're basically going to pick the zero values. Now, you realize that when I was doing PPS, NPS, I didn't care about all this grounding system of the generator, right? But right now that it has become expedient for me to find X naught, I need to look at the grounding system of the network. So from the network, let me have a quick draw here. We have a generator connected to a transformer, through to another transformer, to one motor here and another motor here, motor A and then motor B. And this has been given as star grounded. Let's look at that, star grounded with a reactance, right? So we have this as with a star grounding reactance. We have this as a delta star grounded system. Then we have this as a star grounded delta system. And this motor, realize that it's actually motor A. This motor A is ungrounded. So this part is ungrounded. and then motor B has a star point grounded. B has a star point grounded. So let me draw my zero phase sequence diagram. So I'm going to start off with the generator. The generator is star grounded. Here is J0.516. So I'm going to bring the reactance. I'm going to connect it to the line because it's grounded first and bring the reactance of the generator. Then I bring three times of the J0.516 into the zero phase sequence diagram because the reactance is inside the star point. So it will be in zero phase. Good. Then I go to the transformer. Now the transformer, we have learned that we are going to use this basic diagram, a diagram like this, where this is for the star, this part is for the delta, and then the reactance of the transformer here, this part for the delta, and this part for star. So if it's star grounded, I'm going to close this. This is for delta, this is for delta, this is for star grounded, and this is looking at the primary side, and this is the secondary side. So let's look at the first transformer. The primary side is delta. So I'm going to open this switch and close this. I'm going to open this switch and close the delta switch because it's delta. And I bring the reactance of the transformer. Then I get to the secondary star grounded. So I'm going to open the delta side. I'm going to open here and close the star side. Good. Then I get to the reactance of the line. Then I get to another transformer. The other transformer is star grounded, so I'm going to close the series switch. I think we have extensively looked at that. Close the series switch, then I bring the reactance of the next transformer. Then the secondary is delta, so I'm going to close the delta switch and leave this place open, right? Then I basically get to my two motors. Now, with my two motors, both of them are here like this, but don't forget that generator A, generator A, no matter where you put it, because they are all in parallel, is not grounded. So you leave this one open, then you draw your line, you leave this one open before you bring the reactance here, and then you bring the reactance of the other one. You connect it to the line because this one is star grounded, right? So we put this together before you come and connect it to this. Now notice that this value is for generator A, and generator A, the X naught was given as J0.345. Here I was drawing the A here, right? So 0.345G, and then the reactance here was given as J0.9. Now notice that the fourth point is after the transformer. The fourth point is after the transformer, which is here, right? After the transformer, which is here. So realize that in case of any fault, it's just basically going to pass through the J0 point now and get here. So it happens that X naught, you see any fault here will not get any chance to go, or this will not get chance to go because of the opening here. So it will end up that X naught will just be J, this was given as J0.69. So this is J 0.69. So this is our X naught. So we did all this long story, but you need to do them so that you know how the connection is. Then later we got to know only this reactance will appear in X naught. So we now have X1, X2, and X naught. We are basically going to go back here and arrange them as expected. So let me have that. I start with my E. Now, you notice that with this power system, everything is given in per unit, right? So because we are going to use the terminal voltage of the generator as the base value, E will always happen to be 1. Then I bring the reactance of X1. I bring the reactance of X2. Then X naught, don't forget there's a 3 times resistance reactance here. And then I'm going to bring the reactance of X naught. So you realize that x1 we got j 0.16, x2 j 0.16, x0 we got j 0.69, but then we realize that the fault had a reactance of j 0.1. So I'm going to bring 3 times that j 0.1 inside where 0 pin sequence is. So this is my line to ground fault diagram. I hope that is clear. And I know here is I1, here is I2, and here is I0. And we know basically that from here, I0 will end up, because my fault current for line to ground also is equal to 3 I0. So I basically need to know I0, right? What will be I0? First, I need to know I1 first before I can calculate I0. I1, this current is going to be, this will give me 0.3. So adding that to this, I'm going to get 0.99, right? So this whole thing is 0.99. J 0.99. So that J 0.99 is going to be in parallel with this and in series with this. So 1 over J 0.616 plus J 0.16 in parallel with J 0.99, right? This part, J 0.99 is in parallel with this and in series with this. E over that will give me I1. So when you point this on your calculator, you are going to get I1 to be minus J 3.359. This is I1. But how am I going to get I0? I0, in terms of current division rule, I0, I1 is total current. So it's going to be the other reactance, J 0.16 over J 0.16 plus J 0.99 times the I1, which we got as minus J 3.359. Now, because of the arrow direction of I0, I need to negate. So it's the negative, this reactance divided by this plus this times the total current. This gives me I0 to be J 0.467. So I have my I0. And since I have I0 now, I can easily find my fault current to be 3 times the J 0.467. And this will give me the fault current to basically be J 1.401. That's all. Nice solution, right? So basically, this is how we solve such a problem. This is how we solve such a problem. Line to line, ground to ground. Now, let's take this same question, and assume that maybe the fault is not a double line to earth fault, but it's rather a line to ground fault. Let's say take the same solution. What it means is that I'm going to go through the same process of finding x1. So x1 remains the same, x2 remains the same, x0 also remains the same. The only thing that is going to change is the final diagram. Because a line to ground fault, the E need to be put in series. X1 need to be put in series with x2, in series with x0, and we need to bring 3 times the reactance, 3 times the J 0.1 here, inside here, right? So our x0 is J 0.69, here is J 1.6, J 0.16, right? And here is, so it's J 0.16. So when it's a line to ground for, the same calculation is going to go on, just that the arrangement of x1, x2, x0 is what is going to change. You realize that the line to ground, we put them in parallel, but this is in series. So here too, we find our I0, and I0 will end up being I1, E1 divided by X1 plus X2 plus X0 plus the 3 times XF, right? So let's find that. I0 to be equal to 1, because it's in per unit, 1 over J 0.16 plus X2 is J 0.16 plus X0 is J 0.69 plus 3 times this, which is J 0.3. So you find I0 will end up being minus J 0.524. Now that I have I naught, in terms of line to ground 2, the fault current is all 3 I naught. Just like the line to ground. The fault current is also 3 I naught. But how we get I naught is totally different when it's line to ground fault, right? So IF will end up being 3 times minus G 0.524. And I'm going to get the fault current to be minus J 1.574. And in terms of magnitude, it's going to be 1.574 angle minus 90. This is the magnitude of the fault current in case it's a line to ground fault. Same calculation, simple steps. Simple steps. Now let's try to take the same question again. And let's assume that this time it's a line to line fault, right? And actually there is no fault resistance. No fault resistance. So we are taking the same question, and this time it's not a resistance, it's a reactance, right? So we are taking the same question, just that we are saying it's a line to line fault and there's no fault reactance. There's no fault reactance. So if it's a line to line fault, I basically need to know that line to line fault, I just need only the PPS connected together with the NPS like this. So I need here J 0.16, here J 0.16, this is 1, and my I1 will end up being E1 over x1 plus x2. So I1 will basically be 1 over J 0.16 plus J 0.16, and I1 will be minus J 0.3125. So this I1, what is going to be my fault current? We said that the fault current for line to line is J root 3 or minus J root 3 I1. So here will be J root 3 times minus J 0.3125. So the fault current end up being 0.541. Simple. Realize that the zero phase doesn't need to come in because line to line, only the PPS and the NPS are available. Zero phase only flows when the fault is to ground. So thank you very much for following the questions on fault analysis. And in the next class, we try to solve some problems on the various things in power systems. So thank you for following this example. You can get any other example and follow the same steps to be able to find the fault current. Thank you and all the best.